All right, so welcome everybody to the talk. As usual, you can ask questions in the Q&A chat on the QIP website, and also at the end of the after the talk, we will move to a separate Zoom room where you can also talk to the speaker afterwards. So without further ado, it will be Anirban Chowdhury, and he will talk about complexity of quantum partition functions.
Thanks, and thank you all for sticking around for the last talk of this QIP. So this is joint work in collaboration with Sergey Bravyi, David Gosset, and Pawel Wocjan. In this work, we're asking this following question, which is, given a physical system, how difficult is it to compute its properties in thermal equilibrium? And this is motivated by the fact that computing ground state energy of, say, local quantum Hamiltonians within some additive error, we know it's hard for the complexity class QMA, which is a set of problems whose solutions you can verify efficiently on a quantum computer. So QMA, in some sense, captures the difficulty of ground state computations of quantum systems. For the corresponding thermodynamic quantities for quantum systems, we're interested in this quantity called the partition function, which is given by trace of exponential minus beta h for some Hamiltonian h, and where this beta is something called the inverse temperature. And we want to know how hard is it to compute this quantity. So in the classical case, we have a very nice characterization. Think of just classical spin systems such as the Ising model. We know that even such classical partition functions can encode very hard graph theoretic problems, such as counting perfect matchings. And this is complete for the complexity class called sharp P. And what is sharp P? Well, NP is the class of all problems which have yes-no solutions, and whose solutions you can verify in polynomial time given the classical computer. And if you now ask the question that, well, how many yes solutions are there to a certain NP problem? This, in rough sense, defines the computational class sharp P. And we know that computing the partition function for classical systems exactly is sharp P hard. Now, it turns out that this sharp P is a very huge complexity class. But if you now ask for some approximation to this classical partition function, in particular, we're going to ask for a multiplicative approximation given over here. This turns out to be a much easier problem, thanks to this nice relation between like the partition function and this counting. There's this fundamental result by Stockmeyer, which shows that we can count the number of NP witnesses approximately given a probabilistic classical computer running in polynomial time and with the ability to query some NP oracle a polynomial number of times. So this BPP raised to NP, it's still a large complexity class, larger than NP, but it's less difficult in some sense than sharp P. It lies in something called the third level of the polynomial hierarchy. And based on the additional fact that computing ground state energy problems for these kind of spin systems is NP complete, we have nice characterizations of the difficulty of equilibrium problems for classical statistical mechanical systems. In the quantum case, this understanding is somewhat lacking. We know that exactly computing the quantum partition function is sharp P complete still. But if we ask for an approximation with a multiplicative error, all we know is this following. We know it's QMA hard because in certain limits, this can recover the ground state energy of quantum systems. And we know that it can be solved in polynomial time if you have access to a sharp P oracle. So this leaves a wide room in between, and we don't know where exactly the complexity of the quantum partition function fits in. This is because we have no known quantum analog of Stockmeyer's approximate counting algorithm. And in some sense, even defining a suitable notion of approximate counting for quantum systems is somewhat tricky, because one way to see it is that quantum states can be continuous because they have complex amplitudes. And there's some caveats here that if we are thinking only of real temperatures, if we allow complex beta and other kinds of error approximations, the problem can be somewhat different, but we won't go there. We're interested in this particular formulation of the problem, given a k-local Hamiltonian, where the locality is in the computer science sense, which means that each term in the Hamiltonian acts non-trivially only on a constant k number of qubits. We want a multiplicative approximation or a relative approximation to the partition function with some precision, which is inverse polynomial. And the question we want to answer is, well, is there a computational complexity class for which this QPF is a complete problem? Unfortunately, we don't resolve this question in our paper, but we make some progress towards it by showing that there are a number of quantum problems that can capture the idea of approximate counting in the quantum world, and which are polynomial time equivalent to computing the partition function approximately. And this is what I'm going to talk about for the next couple of slides. So the first problem that we define is something we call, in fact, quantum approximate counting. So here we have something called a QMA verifier circuit. We have some input quantum state psi. We run some polynomial time quantum computation on it and do some measurement on a single qubit at the end. And we accept or reject the state based on whether this measurement returns us 1 or 0. And a problem is in QMA if there exists such a circuit such that yes instances are accepted with some probability at least A, or no instances are rejected with some probability, which is at least B. And there's some promise on the gap. Now, even though we cannot count, say, quantum states in some sense because they're continuous, we can now say, well, we can ask, what is the dimension of this space of states that is accepted by this QMA verifier circuit? And formally, we can define this by noting that this entire circuit, U followed by a measurement, defines a generalized measurement, or a POVM, with two elements, A and I minus A. And we can now ask, well, the dimension of the subspace spanned by eigenvectors of A with eigenvalue greater than lambda is basically the dimension of the subspace, dimension of states which are accepted by this measurement with that probability. So this is something we can count. And this is, in fact, a notion of counting that was defined in this paper by Brown, Fleming, and Shook. And we define an approximate version of this by saying we want to return an estimate n hat, which is between these two thresholds. And here we have NA on the left-hand side and NB on the right-hand side. This is just saying that if we have a state that kind of falls within this gap, we can miscount it, and we don't care about that. And we show in the first result in our paper that if you have an oracle which solves the two local quantum partition function problem, that is QPF for two local Hamiltonians, this can in fact solve QSE, that is approximate counting. And the proof idea is fairly simple. We use a circuit to Hamiltonian construction such that all accepting witnesses corresponds to low energy states of the Hamiltonian, and all orthogonal states that come in through this Hamiltonian construction get some sort of energy penalty. Then we define an additional problem, which is also a version of approximate counting. Here we ask the question, given a local Hamiltonian, and in some small interval in its possible range of eigenvalues, what are the number of eigenvalues lying in that interval? We call this the quantum density of states. And we show that having an oracle for QAC can in fact solve this QTOS problem. Now, you can believe me if I say that if you have the ability to split your energy interval into small number of small intervals and enumerate the number of eigenvalues in each of them, you can patch them up to recover the partition function of the same Hamiltonian. And this shows that if you can solve this QDOS problem, you can solve K local QPF. And by doing so, we've also shown that if you can solve QAC, you can also solve two local QPF. And as an additional result, we show that computing thermal expectation values of local observables within some additive error, this also formally reduces to solving the K local QPF problem. So in summary, we establish these following equivalences in our paper. We showed that the QPF is polyton equivalent to these three problems. But this leaves open the question, well, what is the complexity of the quantum partition function? And the hope is that one of these problems can now be used to define a sensible complexity class which captures the complexity of computing this partition function. So now, based on this previous few slides, we understand that computing this partition function, approximating it, is pretty hard, though we precisely don't know how hard. But in certain special cases, there are known to be efficient approximation algorithms using a wide variety of techniques, some of which I've just listed here. In another result in this paper, we show that there is an efficient algorithm for a new class of certain dense local Hamiltonians. And this efficient is with a star because we are going to slightly redefine the problem. We will not think about the partition function directly, but instead compute its log or something called the free energy, this F here. And we'll think of only two local interactions, n-qubit Hamiltonian with two local terms. And our goal will be to estimate the free energy within some relative error. We return an estimate F star, which is epsilon times the sum of all the norms of these terms in the Hamiltonian. For instance, if the Hamiltonian has all-to-all coupling, so every qubit talks to every other, and each Hij has norm at most 1 over n, we get an error, additive error that is extensive, that it scales with the system size. So in particular, this kind of error is not sufficient to return return a multiplicative approximation to the partition function. That's why I say it's a slightly different problem. And we'll make a further restriction, that is the Hamiltonian is dense, which means that we have almost all-to-all coupling. So this graph denotes where every qubit lying on a vertex is interacting with every other via this edge denoting an interaction. If we now remove a few of these interactions or these edges, we get a dense graph or a dense Hamiltonian. And we're going to solve the free energy problem for such a graph. And just to give a bit of context, we believe that approximating ground state energy within this kind of relative error for some epsilon is also QMA hard. This is based on something called the quantum PCP conjecture. But despite this presumed hardness of the general problem for general local Hamiltonians, we know that for dense to local Hamiltonians, there exist efficient approximation algorithms to estimate the ground state energy within similar error. And our work you can think of as being extending this to the more general problem of free energy. And we use certain different techniques, but we build on some of the ideas in this prior works. Now, result is as follows. We give an algorithm for this problem, a classical approximation algorithm, which runs in time, which is n raised to 1 over epsilon squared. So if we ask for a constant epsilon approximation error, we get an algorithm that is polynomial time. But again, this is not sufficient to solve the original QPF problem I had defined. And our algorithm is based on the variational characterization of free energy. That is, we have something called this free energy functional, which is the sum of the average energy term and something depending on the von Neumann entropy. And if you minimize this function over the space of all density matrices, this gives you the free energy. Now, this is an optimization you can in principle do, but you cannot do it in practice because this minimization is over exponential sized matrices if you have an n-qubit system. So our optimization is too difficult. What do we do? Well, we solve an easier optimization problems by using the idea of convex relaxations or SDP relaxations in this setting. And the idea is that we only store reduced density matrices. We store reduced density matrices on small subsets of size much less than K. And we store local marginals, or say these two systems, and with the condition that they must be locally consistent. And we store all such possible marginals. So if you have K equals 3, we're going to store marginals on everything up to 3 qubits. That's the idea. And the key point which makes this a relaxation is that these marginals may not be consistent with the density matrix on larger subsystems. So if you now ask, is there a density matrix defined on this entire subsystem? The answer will be no. And this is because even if we store just marginals, ensuring that they're consistent is in fact a QMA hard problem in general. And we don't want our optimizer to be solving QMA hard problems and at intermediate steps. So the relaxation is that we are relaxing global consistency of local marginals. And this allows us to store these, have an efficient data structure. If we just keep K qubit marginals, we can store them as an object of size that goes roughly as this. So if K is not too large, we are safe. And in terms of these local reduced density matrices, we're going to define a relaxed objective function, which we will minimize. But the issue will be that since we have relaxed global consistency, we might get a set of inconsistent marginals, and therefore we will be out of the feasible set. So the minimum we get, the value of the functional, this may not correspond to a valid free energy. So what we do is we take these inconsistent marginals, do some patching up to return a global quantum state. And this is something called a rounding map. And in this work, we're building upon results for the classical Ising model by Risteski. And in a little more detail, what we have is we have this difficult minimization. We're minimizing some functional f over this set of density matrices. And we're going to find an easier version where we minimize a relaxed objective f tilde. And this f tilde will be designed in such a way that it's in some sense a lower bound to this function f if you evaluate it on valid density matrices. And it'll be convex so that we can run convex optimization. So if you now do this relaxed optimization problem, we're going to get a lower bound to the free energy. But the issue is we won't know how far this lower bound is. And to fix that, we have this rounding map where we take whatever set of inconsistent marginals that minimize this relaxed functional and patch them up to return a valid density matrix. And the cool thing is that the error that we incur in this rounding step, so f0 minus f star, that will be bounded by some epsilon. And by the variational principle, we know that the true f we want is the minimum of this f, and therefore it must lie somewhere between. So this is how we're going to ensure that our approximation that we get from the relaxed program is a good approximation. Now, you can believe me when I say that the energy part of this free energy function is something you can compute if you just have access to local marginals. The issue will be the entropy, which depends on the full density matrix, its trace of rho log rho. And to fix that, we have to define something called a pseudo entropy functional, which is almost like a mean field entropy, but instead of just being mean field, it also has some kind of conditioning. It's a sum of the entropy over some small subsystem C of size less than k-1, plus a bunch of conditional entropies, where the conditioning is on the set C. And the nice part is this is something we can compute if we just have access to local marginals. And we can prove by properties of the quantum entropy that it's a concave function of marginals and upper bounds the true entropy. And this will ensure that the pseudo-objective F tilde we construct is convex and will lower bound the true objective that we want. So this will give us a valid relaxation. And I'll just briefly talk about how we round this. And to think of the rounding, we'll consider instead of doing the entire thing over just classical probability distributions, not density matrices, to make life simpler. And if we do some kind of analogous minimization over a collection of now k-local marginal distributions, classical probability distributions, we'll get a bunch of marginals which may not be consistent with the global distribution. And the patching up, something called correlation rounding defined in these papers, is done in the following form. We pick a random subset C of size less than k-1, sample some assignment of the variables in it, which we call xc, dictated by the local marginal defined on C. Then, conditioned on this xc, we sample a different variable 1 and get some value x1. And we keep repeating this kind of conditional sampling, with the conditioning being on this outcome xc we've obtained on C. And we do this for all variables that are not in the set C. And once we do this, we get something like a distribution that is an almost product distribution, where all the variables that are not in C are correlated with the variables in C through this expression, but they are conditionally independent. So if you condition on this outcome xc, a pair of variables ij that are not in C are independent. And the intuition behind doing this is that, well, this gives you a valid distribution from your global valid distribution from your sets of inconsistent marginals. And the nice part is that we can show by some precise bounds that conditioning on a small subset of variables in this form makes the others almost independent, by formally showing that the mutual information, the conditional mutual information can be made small. And as a consequence, you can show that the error you incur in your rounding error, which is how much your two local marginals change, goes down as 1 over square root of k. And to now make this work, we encounter some technical difficulties in the quantum setting, which is that quantum condition is difficult. You cannot just condition on the outcomes of some kind of measurements on an orthonormal basis. What you need to do is use something called an informationally complete POVM, convert your density matrices to distributions, apply the previous slide's arguments in the space of distributions, and convert back to a global density matrix. And then you need to make sure that in this conversion, your small errors in the distributions don't blow up. Finally, we need to prove an entropy bound, because all that I said in the previous slide only works for the energy term. To make things work for the entropy, we need to do some additional step, and that's also something we prove in the paper. And finally, we need to make sure that in this setting of reduced density matrices, there are that the theorems about convex optimization actually work through. And all this we prove in the paper, and I won't tell you about it, but please feel free to ask me questions later. And as we get the following result, and I'll just mention some quick implications. The algorithm itself just runs convex optimization over sets of marginals. The rounding is just to show a rigorous error guarantee. Further, if you forget the entropy part, this also gives an algorithm for approximating the ground state energy of this Hamiltonian. And it's somewhat different from previous work in that previous work basically goes by showing that there exists a product state and then optimizes over the set of product states to find that one to give a good approximation. Here, we have, in some sense, a more direct algorithm. So that's what I say in this slide. And the general idea for here is that you forget global consistency at the outset and impose it later through this rounding map. And there was a bunch of similar works at this QIP using similar ideas of these SDP or convex relaxations for these quantum ground state problems. And as a quick summary of the results, I talked about 1 and 2 here. We also have some other results on improvements to other exponential time algorithms. I didn't talk about it, but if you're interested, here's a link to a talk I gave recently. With that, I'll end my talk by showing some open questions. Thanks.
Thanks. So there's a question by Robin Kotari. He's asking, in your definition of the quantum partition function problem, what is the allowed range of beta? Is there some range of beta where the problem's complexity is fully understood?
Yes, so we ask for beta to be like polynomial in n. And as I said, if you allow beta to be complex, we know that it's sharp B. Beyond that, I'm not sure, at least for the multiplicative approximation. For additive error approximations, there are other results.
So I was wondering, you said that in this, so this free energy has a variational characterization and it involves entropy. And I was wondering, like, is that not causing some trouble because it's not a linear function? Like,
yeah, so I mean, that's the relaxation. We basically, just see if I can scroll through. So that's why we use a relaxation for the entropy, which is this thing over here.
But doesn't that also involve other entropies?
I mean, as long as we have the guarantee that it's a convex set, I think the theory that like the theorems that rely on for convex optimization we go through, as long as you have a convex function.
Oh, I see. You just convexity. I see.
Yeah.
And why is the denseness necessary? Like your
yeah, good question. So that's necessary for this correlation rounding step. So here we need to average over all possible choices of the set C. Only then does this mutual information, conditional mutual information argument go through. I mean, not we, it's in this paper by Yoshida Zhu. So only if you average over all possible choices of the set C and all possible sizes of the set C up to K, will this thing become small. That's why you need like a complete graph, and a dense graph is basically showing it's close to a complete graph. That's why you need it.
There's another question. Do you have a hunch for what the complexity of QPF might be? Do you think it's close to Sharpie or much easier?
I guess, yeah, I guess I personally would not know. We speculated it should be something easier, but I don't think we have a good understanding of it yet.
And have you sort of quantum algorithms for this problem also?
Not for this particular problem, but I have some prior work on like quantum algorithms for solving partition functions within additive errors. But those are like exponential time algorithms, not polynomial time ones.
All right, I think we should wrap it up. So you can always come to the Zoom room for the Q&A.